And then once that slot is filled out, then it's only the leftmost or the rightmost of what remains goes. And so we get a nice binary tree out of this. These are the initial, if you follow from the initial node down to the leaf at the bottom, those are all the possible binary tree paths. Okay, so we can see there's 2 to the k minus 2 of these initial candidate permutations. And there's a natural binary encoding. I mean, you just go from 0, all zeros up to 1, 1, 1, 1. And so taking advantage of that, I want to call p sub j denote that particular candidate permutation in the sense that for k equals, in the k equals 5 case that we're just looking at, we've got 1, 0, 1. That would mean start at the top, then go, for every time you have a 1, you go right. Every time you have a 0, you go left. So right, left, right. And so, there we go. So 1 right, 1 left, 1 right, and then there's only one choice left, and you just fill that out. So that's that. So you can call that P101 or in binary or P5. So what we're going to see in a moment is that there's among these candidates, the ones that actually turn out to be optimal tend to be on the right, and we can actually weed out, even our initial weed out from k factorial down to 2 to the k minus 2 choices. Well, it turns out a lot of these can't possibly work either. So how do we do this? We use high school algebra in accordance with opinion number 74, of course, with your favorite computer algebra system. So many candidates can be weeded out from these initial candidates just by looking at adjacent nodes at the bottom of the binary tree. So you can see that P1 always dominates P0. So this is the far left, and this is 1 over from the far left. If you just work out by computation what the polynomial is and factor it, you see, well, the b's are all positive, and because of in the degree sequence, they're weakly decreasing. This is not negative, so you get greater than or equal to 0, so P1 is always bigger than or equal to P0. Similar thing happens, P2 is always bigger than or equal to P1, and it turns out I didn't put it on the slide, but P3 is always bigger than P2. So there's a lot of cases where this happens. And as it turns out, the initial weed out set goes 2/3 of the way across the tree from the left. Now, it's not it's a subset of this, to be fair. It's not all of that. But it's a proper subset, and this number, or this entry is always present there, this exact number that I have in the end. And that's kind of it's an interesting sequence, which I'll mention in a second. The cardinality of this proper subset is this number. Okay? Now, so both of these, as you let k increase, are in Neil Sloan's encyclopedia. So the first one has a number of combinatorial interpretations, but one of them is it's the gray code that has all 1s with k minus 2 digits. And there's another interpretation in terms of minimal vertex coverings, and we haven't figured out what the exact connection to the problem is yet, but there's got to be one. And as far as the cardinality of the set, that's also in Neil Sloan's encyclopedia, and this has to do with, it counts the number of symmetric dict paths. And once I brought this to Hua's attention, and he said, oh yeah, look at that, I could see the symmetric dict thing, so he can do that kind of stuff. Anyway, and another thing I learned from Doron is you're supposed to thank and mention people that you expect will be in the audience. And so I want to say thank you to Neil Sloan. He was here yesterday. I don't see him here today, so we move on quickly then. Okay. All right. So now also we can do some more of this high school algebra weed out with non-adjacent pairs sometimes. And there are certain conditions that seem to give rise to that I'm not having to get into. But P11 always beats P7 for large enough k. I mean, you have to have k bigger than 4 for this to make sense, and so on. So now the maximality characterization. So this problem has been looked at before. In fact, there's a paper on the archive a little under a year now, and by Zhang, Liu, and Han. And they didn't use this binary tree notation, but translated into the notation that I've showed you. They proved that for k equals 4, that the one on the P11, so that's P3, that's always maximal. For k equals 5, there turn out to be 3 cases. So this one is the far left, so P7, when you have this condition, P6, so 1 over from the, I'm sorry, I said far left, I meant far right. So the far right is maximal, or 1 over, 1 left of the far right is maximal under this condition, and there's a tie when you have kind of the bordering condition. They also did k equals 6. There's 11 cases, which I won't go through in detail, but you can get the general flavor of them, and you can see we're always sort of hovering near the far right of the table, and we managed to get a little bit left, but not never more than the 2/3 mark in. They stopped at k equals 6 and said, this appears to be hard, basically. I'm paraphrasing. So I decided to shalosh it, and I could see why they stopped, because they apparently were not shaloshing. And there are 1,312 cases. So I have them on my computer if anyone wants to see them later, but I'm not putting them up on the slide. I have not attempted to work k equals 8. This is, in fact, k equals 7. This took a couple of hours of computer time, just on my old PC, or my old laptop. And k equals 9, I really don't have much hope for. I'm going to try k equals 8 at some point after the conference. And another important rule is when the moderator is standing up, then you know you wrap things up because we don't run over. So it's better to skip these slides. If anyone sees anything interesting, you can ask me about it later. And just say, happy birthday, Doron. Thank you.
Questions? Can you hope to get approximate algorithm for that technique?
Can always help. Yeah. This is very much a work in progress. I've just been working on it for the last less than 2 months.
And you have it completely for 7. Okay, for 7? You have
I believe so. Although I haven't read all through all 1,300. There could be a bug. I have to, you know. But there's much more work needs to be done.
I think your theorem about the Wiener index implying counterply by, I think, Frank Harari.
Thank you.
So then, do the nice, the optimal trees have any special structure? Kind of figures? So do you know the optimal tree?
So yeah. So these give. So in what sense? I mean,
You're maximizing the Wiener index.
Right. So
the answer is a tree.
Right. So the answer is a tree. So each of those p sub things that represents a particular degree sequence.
Yeah.
And so that's the tree. So under the conditions like if b1 minus b2 minus b3 is greater than 0, then you have that then you have this one tree. You have another tree is maximal under other circumstances.
So do you have any structure? If you look at what's happening from k from 1 to 7, can you find any structure?
Well, I mean, other than the characterizations that I showed you, I mean, I'm not sure I understand the question.
Okay, I'm not sure.
Okay. Remember, I don't know anything about this really. So.
Right, let's thank the speaker.
All right, thank you.